Today is the first lesson of Unit 3, titled Solving by Factoring and Completing the Square. You're going to go ahead and get started on your warm-up for today. Given the functions f of x and g of x, please go ahead and graph it on the coordinate plane given to you below. Please pause the video at this time and resume when you are done graphing both f of x and g of x. This is a graph that you should have gotten for f of x. As a reminder in terms of strategy on how to solve this, I always recommend graphing quadratics by first identifying its axis of symmetry using the formula x equals negative b over 2a. We end up finding our axis of symmetry is x is equal to negative 1/2 given the function rule x squared plus x minus 6. And the variables a and b come from standard form, ax squared plus bx plus c. Once identifying the axis of symmetry is x equals negative 1/2, we can then find where the vertex is located by substituting in negative 1/2 into the function rule. Negative 1/2 quantity squared plus negative 1/2 minus 6 gives us a vertex located at negative 1/2, negative 6 1/4. When the equation is given to us in standard form, we're able to use the c value to identify the y-intercept. If we have a point located at 0, negative 6, we're able to also reflect that point half of the unit away from the axis of symmetry on the other side to find that negative 1, negative 6 is also another point that exists on our parabola. From this point, once we have several inputs and outputs, we're able to simply just find a couple more x values to reflect over. So find when x is equal to 1, its corresponding output, when x is 2, when x is 3, and then reflect those points over to the other side of your parabola. Algebraically, you would find x is equal to 1 has a y or output value of negative 4, 2, 0, 3, 6. Once you have those 3 points, you can also reflect them on the other side to find negative 2 has an output of negative 4, negative 3, 0, and negative 4, 6. Similarly, to graph the function g of x, my hope is that you started with the axis of symmetry, x is equal to negative 5 divided by 2 times 2, to find an axis of symmetry of 5/4 or 1.25. Once you identify your axis of symmetry, our next step would be to identify its vertex, located at 2 times 5/4 quantity squared minus 5 times 5/4 minus 3, to find a vertex located at 1 1/4, negative 6 1/8. Although this is slightly harder to reflect points over, my recommendation would be to then use the c value to find the y-intercept point, and then simply just plug in using a table of values several x and y values. Negative 2, negative 1, 0, which we already know is negative 3, 1, 2, 3, to finish the rest of your graph of your quadratic for g of x. At this time, please go ahead and check your answers for the rest of the warm-up. We know that the definition of roots is solutions of x when y is equal to 0. So when y is equal to 0 along this axis, we can identify its roots by finding the two solutions of x. One solution of x is x equals negative 3. The second is x equals positive 2. For the function g of x, looking along the x-axis, one of the roots I can clearly identify is at positive 3. However, the second root is not an integer. It's somewhere between the values of 0 and negative 1. So this currently is unknown. The next part of your warm-up, you were asked to factor. As a review from last unit, hopefully you were able to take the quadratic 2x squared minus 5x minus 3 and factor it either using the box method or guess and check. My hope is that you were able to identify a relationship between the roots and its factored form. As a reminder for the definition of roots, solutions of x when y is equal to 0. We have the factored form for the function f of x, and we can see that x equals negative 3 is probably related to the factor x plus 3, and x is equal to 2 is related to x minus 2. Using the definition of roots, solutions of x when y is equal to 0, we're able to substitute in 0 for f of x, set 0 equal to x plus 3 times x minus 2, and then solve algebraically for the two values of x. I know that x plus 3, setting that equal to 0, will give me x equals negative 3, which is one of the solutions. X minus 2 equal to 0 gives me x is equal to positive 2 as the second solution. So in order to find the unknown non-integer value for the second root of g of x, what we can do is take 2x plus 1, set this root equal to 0, set this factor form equal to 0, and solve algebraically. 2x is equal to negative 1, so our root is x is equal to negative 1/2. We know that the second root, x is equal to positive 3, should also match if we set x minus 3 equal to 0, and we do find that x is equal to positive 3. The reason why we're able to set each factor individually equal to 0 is because of the zero product property. The zero product property states that if a times b is equal to 0, then either a is equal to 0 or b is equal to 0, or both a and b are 0. When the product of factors equals 0, one or more of the factors must also equal 0. Once the polynomial is factored, set each factor equal to 0 and solve them separately. Product property is not limited to just 2 factors. We can have 3 factors or 4 factors or even more than that. For now, because we have quadratics in general, it's just a times b is equal to 0. However, you can also see here that we can have a times b times c being equal to 0. As long as just one of the factors are equal to 0, then the entire result will equal 0. This logically should make sense to us. If the value for a is equal to 0, it doesn't matter what b is equal to. B can equal 10 or 20 or 30, because 0 times any number will always give us a result of 0. So for this instance, the quadratic is x squared plus 2x is equal to 0. X is either going to equal 0 or the factor x plus 2 equals 0. So the two possible solutions of x is when x is equal to 0 or when x equals negative 2. We should be able to also check our work for this. If I plug in 0 for x, I end up getting 0 times 0 plus 2 being equal to 0. I know that 0 times 2 is equal to 0, so we know that x equals 0 is one possible solution. The other solution we found was x equals negative 2. Negative 2 times negative 2 plus 2, check to see if it's equal to 0. I know that negative 2 times 0 is equal to 0, so yes, this is also the second solution for this example. The following 4 examples ask you to find the roots using the zero product property. Remember, the zero product property does require that you have factors, so we will do one example together for t of x. T of x is equal to 6x squared plus 5x minus 4. You are more than welcome to use any method that you want. I'm going to use the box method, but you can also use guess and check as well. So using the box, inputting the 6x squared, the negative 4, and trying to find two terms that will break up to add to 5x. I also want the product of my diagonals to be equal to one another, so the second diagonal has to also multiply and equal negative 24x squared. Finding factors of negative 24x squared that multiply to this value and add to positive 5x. Positive 8x times negative 3x is equal to negative 24x squared, and the sum of these two also add to 5x. Placing those terms into my box. Then factoring the GCF from every row and column. From the first column, the GCF is equal to positive 3x. From the second column, my GCF is equal to positive 4. From my first row, the GCF is equal to 2x. And from the second row, the GCF is equal to negative 1. Make sure that everything multiplies back in to the box. 2x times 3x is 6x squared. Negative 1 times 3 is negative 3x. Negative 1 times 4 is negative 4. And 2x times 4 is equal to 8x. So these are the two factors of the function t of x. T of x equals 3x plus 4 times 2x minus 1. The zero product property states that as long as one of the factors are equal to 0, then the equation will equal 0. So I'm going to set 3x plus 4 equal to 0, 2x minus 1 equal to 0, and solve for what my two roots would be. 3x equals negative 4, so one root is negative 4/3. 2x is equal to positive 1, so the second root could also be x equals 1/2. So the two solutions, x equals negative 4/3 or 1/2. Please go ahead and do the other three examples, and pause the video at this time. The solutions for number 2 for k of x is equal to negative 7 or 4/5. For example 3, the solutions are x equals negative 3/2 or 7/2. And for number 4, what you should have found once you factored out the GCF is that the trinomial x squared minus 4x minus 13 is not factorable further. There are no rational factors. However, just because this function is not factorable any further does not mean that this parabola does not exist, nor that it's not real. I know that this parabola can be graphed on a coordinate plane and it will have roots. My y-intercept is located down at negative 26. I know that this is an upward facing parabola because I have an a value of positive 2. So this is a very quick little sketch of what my graph will look like. It's very clear here that I do have two roots that are real. They have real roots, but they are just not rational roots. Again, this function a of x has real roots. Because we're not able to solve this using the zero product property or a factoring method, we need to use another method. And the second method that we're learning today is a method called completing the square. Our objective on this page is to still find the roots of the same example, number 4 for a of x that was on the previous page. A of x equals 2x squared minus 8x minus 26. But this time we're just using a different method called completing the square. Please follow along as I go through step by step exactly how to solve this problem. The very first step that we do is to group the variable terms together. The variable terms in this equation would be the 2x squared minus 8x. Once I group the variable terms together, what I want to do is factor out just the leading coefficient. This is different than factoring out the GCF. So when I factor out the leading coefficient, I end up factoring out 2, and what remains is x squared minus 4x. The constant, negative 26, will stay the same. The next step is called completing the square. To do so, what I'm doing is taking the value of b, which is negative 4, dividing that by 2, which gives me negative 2, squaring it, and adding it inside of the parentheses. So b divided by 2, quantity squared, becomes positive 4, and I'm adding 4 to the equation. However, I can't just add 4 and change the value of this expression. I actually have to make sure that I balance this equation by also subtracting the same exact value I added. I didn't necessarily add 4 to this equation because it's technically 4 times 2 that was added. So to balance it, I have to subtract 4 times 2, which is 8. Technically, by doing this, what I've done is added 8 to the equation, subtracted 8 from the equation, so 8 minus 8 would essentially be 0. So this entire line is equivalent to the original function that I was given. My next step is to factor this perfect square trinomial. When I factor x squared minus 4x plus 4, the two factors would be equivalent to x minus 2 times x minus 2. Every single time you complete the square, you will always end up with a perfect square trinomial. For example, x minus 4 quantity squared is a perfect square trinomial. It's x minus 4 times x minus 4, which is equivalent to x squared minus 8x plus 16. So is x plus 3 quantity squared, as just random examples I'm putting out there. X plus 3 times x plus 3 is equivalent to x squared plus 6x plus 9. The pattern with perfect square trinomials is that the b and the c value are related to one another. If you take a look at the value of b, which is negative 8, negative 8 divided by 2 is equal to negative 4, and negative 4 quantity squared is equal to positive 16. The same goes with x squared plus 6x plus 9. I know that this is a perfect square trinomial because the value of b, which is 6, divided by 2 is equal to positive 3, and 3 squared is equal to positive 9. Anytime you end up with b divided by 2 quantity squared being equal to c in the form ax squared plus bx plus c, you'll end up having a perfect square trinomial. The factors will always be equal to x minus half of b, x minus half of b. So you'll notice that from the example x squared minus 4x plus 4, the two factors, I knew that it was going to be x minus 2 times x minus 2 because half of the b value was equal to negative 2. Now continuing this process, finishing it up, a of x is equal to 2 times x minus 2 times x minus 2 minus 34. Instead of rewriting x minus 2 times x minus 2, anytime we have a perfect square trinomial, we're going to write it as x minus 2 quantity squared. 2 is still the leading coefficient that was originally factored out. The constant is still negative 34. And once I have my factored form for my perfect square trinomial, then I'm going to set this equation equal to 0. I'm setting the equation equal to 0 because my goal is still to find the roots of this quadratic, and finding roots are solutions of x when my y value is equal to 0. So from this point, all we're doing is solving the rest of it algebraically. My goal is to keep the x minus 2 quantity squared by itself on one side of the equation, so I'm isolating the squared binomial by first adding 34 to both sides. 34 is equal to 2 times x minus 2 quantity squared. Dividing both sides by the leading coefficient, 17 is equal to x minus 2 quantity squared. Then I'm taking the square root of both sides. Last unit, we learned that when you have an even exponent under the radical, the index is even. In this case, it's not written, but we know it's a square root, so the index is 2. And the variable comes out odd, then it will require absolute value. So this technically turns into x minus 2 with an absolute value, and this is equal to the square root of 17. To solve this absolute value equation, I have two different solutions. I know x minus 2 is equal to the square root of 17. So one possible equation would be just x minus 2 is equal to the square root of 17. And the second equation would be negative x plus 2 is equal to the square root of 17. Solving this, x is equal to positive 2 plus the square root of 17. For the second equation, negative x is equal to negative 2 plus the square root of 17. Divide both sides by negative 1, and x is equal to positive 2 minus the square root of 17. There were a lot of steps to this problem, which have all been written out for you, so at this time, please pause the video and copy down steps 1 through 7. The reason for the second column is because I'd like you to get more practice on your own, so please try covering the left side and retrying the problem on the right side following each one of the steps that were listed previously. When you're done with this problem, go ahead and remove your hand and compare each step to the example that we did together. There are 3 examples remaining on your handout. We're going to do the middle one together for the function s of x, and the other 2 you're going to be doing on your own. So taking a look at s of x, we know that 4x squared minus 7x minus 1 is not factorable. Therefore, we're going to solve it by the method of completing the square. So step number 1 is to group the variable terms together, 4x squared and negative 7x. Step 2 is to factor out the leading coefficient from the variable terms. So factoring out 4, I get x squared minus 7 over 4x, isolating the constant, negative 1. Step 2 is to complete the square. I'm going to take the value of b. Half of this would be negative 7 over 8. Square it, and I end up with positive 49 divided by 64. I technically added 49 over 64 times 4 to this equation. 4 times 49 over 64 is equal to 49 over 16. So I want to rebalance the equation by also subtracting 49 over 16. Step 3 is to factor the perfect square trinomial. So x squared minus 7 over 4x plus 49 over 64 in factored form is equivalent to x minus 7 over 8 times x minus 7 over 8. It's not necessary to write out both factors in this way. We can rewrite it as just x minus 7 over 8 quantity squared. This is equal to 4. And just to rewrite my constants together, I'm going to just find a common denominator. Negative 1 is negative 16 over 16 minus the 49 over 16 gives me negative 65 over 16. My next step is to set the equation equal to 0 since my objective is to find the roots of this quadratic. Then continuing on to solve algebraically by isolating the squared binomial. So adding 65 over 16 to both sides of my equation. Then dividing both sides by 4. Dividing by 4 is the same thing as multiplying by 1/4. So 65 over 64 is equal to x minus 7/8 quantity squared. Then solving this further algebraically, I can take the square root of both sides. I know we haven't really talked about this yet, but when you have a fraction and you're taking the square root, you can take the square root of both the numerator and the denominator. So the square root of 65 cannot be simplified any further. It's just the square root of 65. However, the denominator for the square root of 64 is equal to positive 8. This is equal to the absolute value of x minus 7/8. Then I know I'm going to end up with 2 different equations. X minus 7/8 is equal to the square root of 65 divided by 8, or negative x plus 7/8 is equal to the square root of 65 over 8. Finally, to find the 2 roots, x is equal to positive 7 over 8 plus the square root of 65 divided by 8. For the second equation, I could add x to both sides and then subtract rad 65 divided by 8. So the second solution would be x is equal to 7/8 minus the square root of 65 divided by 8. Please go ahead and do the following 2 examples on your own for m of x and q of x. Go ahead and pause the video at this time, and when you're ready, go ahead and check your answers by pressing play. The answer to m of x is 4 plus 3 times the square root of 5, or 4 minus 3 times the square root of 5. Just a reminder of what we've been doing this entire time. We're taking a quadratic function and we're trying to find the roots of this quadratic. Because it's not factorable, we know that it will have irrational roots, meaning that it still does cross the x-axis, it's just not going to happen at an integer. So for this example, if I were to do a quick sketch, I know that my y-intercept is down at negative 29. And I know my two roots will be approximately negative 2.71 and positive 10.71. So this is a very rough sketch of what my graph will look like. I also